Hello everyone, welcome back to the next lecture in our blockchains course, Architecture, Design and Use Cases. So in this lecture, we're going to delve into Hyperledger Fabric itself and look at the transaction flow that we have, right? And look at some of the key concepts, how a transaction is going to get committed by all the peers in the blockchain network in a consistent manner, right? So we need everyone to be committing the same transactions in the same order, and we're going to talk about how we achieve that in a completely decentralized fashion. So let's look at the high-level architecture. So what are the key components of the Hyperledger Fabric architecture itself? So let's start from the top, right? So there is a membership service. Like I mentioned, this is going to be providing the notion of identity for the users who are going to be transacting on the blockchain. So this identity is going to be a digital certificate, and users are going to be using this digital certificate to sign their transactions and submit them to the blockchain. And the benefit of signing this transaction is twofold. One, they authenticate with the blockchain that they are a legitimate user. And two, it also ensures that they get the right access privileges on the blockchain for the transactions they are performing. Like I mentioned, we do have notions of access control. So certain users are allowed to perform certain transactions. And if you don't have the right access, then your transaction will get rejected. So your certificate is going to have all that information about you, what privileges you can have, what attributes you have, and so on. And we use that to transact on the blockchain. Now, how did this certificate, where did this certificate come from? It comes from a traditional certificate authority. Right? Fabric implements a certificate authority. So this is the Fabric CA, and this certificate authority is optional. So all it does is issue the certificate. So you go to the certificate authority and say, okay, I am Praveen Jayachandran, give me a certificate, and it will then issue the certificate saying this public key belongs to Praveen Jayachandran. Praveen has these following attributes and so on, right? So that is the role of the certificate authority. Then the certificate authority is a pluggable module. So it's very much possible for someone else to bring their own certificate authority that issues certificates. So you can bring in external certificate authorities as well. And the notion of certificate authorities is nothing new, right? The internet uses certificate authorities all the time, right? Whenever you have any secure communication between to a website, you're going to use some notion of certificates. So this certificate authority can be external. There are a large number of organizations that provide these services, and those can be used as well. And all of this relies on public key infrastructure. So you do have a public key and a private key associated with you as a user. The private key needs to be private only to you. So you are the only one who holds that private key. The public key is something that you advertise to the entire world, and the certificate authority helps you advertise that. So to say that you are recognized in this network and this public key belongs to you. And this public-private key pair is used to authenticate with the blockchain. Now the client application can be written in absolutely any language of your choice, and we provide a set of SDKs to interact with the blockchain. So it's called the Hyperledger Fabric Client. This is the HFC. And the SDK today is available in multiple languages. It's available in Node.js, it's available in Java, it's available in Python as well. So you can use any of those SDKs to perform your transactions on blockchain. Now coming to the blockchain itself, what are the various components? The important component is of course the peer. So there can be multiple organizations that are each running one or more peers. So it's possible that one organization runs multiple peers, several reasons, for fault tolerance reasons, for just separating out different applications it's part of. So it's possible for one organization to run multiple peers, and of course there are multiple organizations that are running the network. So that is the peer itself. And apart from the peer, there is an ordering service. So this ordering service can also be run by multiple organizations or one organization. You can architect it however you choose. And then the goal of the ordering service, or the function it provides, is to give you a totally ordered set of transactions. So different peers might be submitting transactions to the ordering service, and the ordering service is just going to take these transactions and put them in some order. And now this ordering service is also decentralized, and the transactions that are coming in from the various peer need to be ordered by this ordering service. So again, it's possible that Some of the peer owning organizations also own the ordering service. That's possible. So they might be the ones running some of these nodes. But just for abstractions purposes, we've kept these as separate functions that anyone can perform. Within the peer itself, there are many notions, right? Of course, the peer is going to be maintaining the ledger. This is the ledger of all transactions, all the state information that is getting stored. It has the smart contracts. We call them chain code. So this is the code that is going to be running on the blockchain itself. So every node in the network will be executing these chain codes. When I say every node, there can be exceptions. We'll come to that. And of course, once the transactions are getting committed onto the blockchain, you can emit events. Those can be integrated with existing systems. Now coming to the peer itself, the peer can have, each peer node can have one or two functions, right? So it can serve as an endorser. What the endorser means is that it is going to execute the chain code. So it has a copy of the chain code with it. It is going to be responsible for executing the chain code and signing the output of that chain code. When I say again sign, this peer also has an identity on the blockchain. It is going to use its certificate to sign this transaction saying, this is the output of the transaction and I agree with this output, right? So that's the endorser. Apart from just signing the transaction, at that point, it's not yet added to the blockchain itself. It has to go to the ordering service. Everyone has to agree that this is a transaction that can be committed onto the blockchain. And once the ordering service comes back with the full order of transactions, then each of these transactions need to be committed onto the blockchain. So this committing function thing is also can be thought of as a separate function. So it's possible that certain peers are both endorsers and committers, whereas certain other peers are only committers. So I might not execute the transaction itself, but whatever other peers have agreed as the output of the transaction, I will only commit. Right? So some of this actually helps in scalability. We'll come to some of those notions. So like I mentioned, some of the roles that organizations can take on is, like I mentioned, all you can be doing is just committing all the transactions that others are performing. So that's a committing peer. So it maintains the ledger and the state, but it does not execute any transactions and it does not hold the smart contracts themselves. The next notion is the endorsing peer. So this is a specialized notion. So beyond just committing all the transactions, you're also responsible for executing the transactions, coming up with the output, and then agreeing whether this is a legitimate transaction or not. So that is the notion of endorsement. And obviously, because you're going to execute the transaction, you need to hold a copy of the smart contract and you need to be executing that smart contract. And apart from the peers, we have an ordering node, which is going to approve the inclusion of transactions into a particular block. So it's going to order these transactions that may be seen across the network from multiple peers, and it's going to communicate to all the peers what is the order in which the transactions must be committed. So the ordering service ensures that all the transactions are totally ordered. Every node in the network is going to commit the same transactions in the same order, and that is what will ensure consistency across the entire network. So if you ping any node, if you ask any node, any peer in the network what the state is, they all have to tell you the same answer, right? It shouldn't be that different nodes tell you different answers, in which case consistency will be lost. And the ordering node, importantly, does not hold a copy of the ledger. It need not even see what the contents of the transactions are. All it will do is just order the transactions in some manner so that all nodes see the same order. Coming to the transaction flow itself, the way in which consensus is achieved is following this order, right? So the client application is going to submit the transaction to a few peers, and these peers are going to execute this transaction and agree that the output is the same across all of them. So they're all going to find the output of the transaction and they will add their signature to it. So that's the part of endorsement. So the client application has to collect endorsements from multiple peers in the network to say that this transaction is a valid transaction and all the outputs are the same. So that's the endorsement part. Once you've collected sufficient signatures, we'll talk about what that sufficient is. Once you've collected sufficient signatures, then you can submit the transaction for ordering. So this now multiple applications might be submitting, multiple users might be submitting these transactions to ordering. And now the ordering service will ensure that all of them are fully ordered, right? And totally ordered across all the nodes. So that's part of the ordering service. So you're going to order the transactions. And once you've determined the order of all the transactions, then there is a notion of validation. So for instance, I shouldn't be performing two transactions simultaneously that modify the same state. So this is equivalent to the double spending problem that you would have seen in Bitcoin. If I have just 10 rupees balance in my bank account, I shouldn't be transferring 10 rupees to two different people trying to double spend that money. So that is the validation part. And you can think of a generalized notion of that, which is for any state, right? Let's say I have a state variable which has the value 100. There shouldn't be two simultaneous transactions, one trying to change that 100 to 200, another trying to change that 100 to 50. Now, if these two transactions are going simultaneously, only one of them can succeed. And which one succeeds will depend on the ordering service. The first transaction that modifies the data element will succeed. Every other transactions in that same block that are trying to modify the same transaction will get invalidated. So that's the validation step. So this is the order in which it's going to execute. So we'll look through these steps in detail now. So the step one of the whole transaction flow is what we call proposing a transaction. So a client application or a user is going to propose a particular transaction. So it'll say, I am this user, I have this identity on the network. I want to invoke this particular function of a smart contract, and here is my transaction. Here are the inputs to that transaction. And this, the client application, will send to multiple endorsing peers. So E0, E1, and E2 in this figure are all endorsing peers. And E0, E1, and E2 are endorsing peers. They will all execute this transaction, but they're not going to commit it into the blockchain yet. They're all going to execute the transactions. And they will say, okay, this is the output I see, and here is my signature. So all these endorsing peers will execute. So that's the proposal part. Now, there is so how many of these peers should I send to, right? The client application needs to determine that, and that is determined by an endorsement policy. Right? The endorsement policy is something that you can define for each smart contract in your network. Right? So for instance, one of the policy might say, I want E0, E1, and E2 to sign for sure. Or I could say, between E0, E1, and E2, if any two out of the three sign, then this is a valid transaction. So there is an endorsement policy that is pre-specified along with the smart contract. And the client application has to satisfy that endorsement policy. It has to communicate with enough peers to gather endorsements for that transaction. Then P3 and P4 in this example are committer-only nodes. So we'll see what their function is over the next few steps. And there is a ordering service that I have shown here. So there's a key here that shows what the difference is. And the pink is the endorsement policy. And here the endorsement policy in this example is to say that E0, E1, and E2 must sign this transaction. So that's the first step of submitting a transaction or proposing a transaction. Now the second step is each of these endorsers, like I mentioned, have to execute this transaction. So the endorsers execute these proposals. So E0, E1, and E2 are going to execute these transactions, and each execution will capture the read and write set. So which data elements were read, which data elements were written is captured by every node in the endorser set. And once they capture the read write set, it is that read write set that the endorsers are going to sign, saying this is what I see from executing the transactions. These three elements were written, these three elements were read, these four elements were written. So that read-write set is collected for that particular transaction, and each endorser will sign on it. Right? So and it can also be encrypted. So all these communications between parties are encrypted for security purposes. Right? So that's the second step of the flow. The third step of the flow is for the endorsers to communicate back the fact that this is the output they see, along with their signature. So the application or the SDK or the client is now going to receive these read-write sets, and all of these are happening in parallel, right? So you can think of these as asynchronous things. So it's possible that E0 and E1 respond first, whereas E2 takes a little bit more time to come back with the response. So all of these are happening asynchronously. And the information, this information about how many endorsements, who signed these endorsements, whether these were valid endorsements, will be checked later in the consensus. So in the flow, we'll talk about when these are actually checked. So this is the third step, where the client receives responses from all the endorsers that it has communicated with. The next step is ordering. So once the client has received some sufficient endorsements that it thinks satisfies the endorsement policy, in this case it needed signatures from E0, E1, E2, it has got responses from all three of them, it is going to then submit the transaction to the ordering service. Now, such submissions to the ordering service can be happening from multiple users, multiple client applications simultaneously across the network. Now, any one node will not know who all submitted transactions, who all submitted other transactions at the same time, right? It is the ordering service that will determine that. So the ordering service might be getting many such transactions from across the network. So that's what is shown here. Other applications are all submitting transactions to the ordering service, and the ordering service is then going to determine how to order these transactions, and it will then make sure everyone sees the same order across the network. So that's the ordering part of the equation. Now, once the ordering service has determined an order, it is going to deliver that ordered set of transactions to all the peers, right, in the network. And this ordered set of transactions is what we are going to call a block. So each block, the ordering service forms the block and communicates that with all the peers, saying these are the 100 transactions which I have ordered. All of you include this block in your blockchain. So these 100 transactions are now part of the block, and they are communicated to all the, and it's possible that these peers themselves are architected in a way that there is a hierarchy. So maybe P4 is part of one organization which has other peers that it also has as committing peers. So this P4 can then communicate to other peers in its network, whereas only P4 communicates with the orderer, right? So it's possible that one peer in the organization takes responsibility for communicating with other peers with the ordering service, but internally all the other peers can then get a copy of the block. Now, how does the ordering service form this ordered set of transactions? Now, this is a pluggable component in Hyperledger Fabric. You can use any ordering service. So there is a rich literature of over 30 years where various consensus algorithms have been designed for ordering and for consensus. So there are a few that are implemented by Hyperledger Fabric today. One is just a solo orderer. So think of it as there is a dictator who's just a single node that is going to dictate what the order should be. And right now that single node implements a FIFO order, a first in first out order. So whatever I see first, the single node sees first, that transaction is going to be ordered first. So that is the solo orderer. The second ordering service that has been implemented is the Kafka ordering service. So Kafka is a very popular event management service by Apache. It's open source again. And internally, Kafka implements a notion of consensus. And that notion of consensus is a crash fault tolerant consensus. You would have seen some of the consensus algorithms in earlier lectures. So what we mean by crash fault tolerant is the consensus algorithm or the ordering service can tolerate certain set of these nodes to fail at any point of time. And even with certain failures amongst these ordering service nodes, you can still achieve consistent order across all the nodes. Right? So that is a crash fault tolerant algorithm. So typically it will say that as not more than 50% of the nodes have failed, I can achieve consensus. Actually Kafka, it will ensure that even if one node is surviving out of the entire network, we can still ensure that ordering is maintained. And here, like I mentioned, it's a pluggable ordering service. So we are working towards a Byzantine fault tolerant algorithm as well. It might come in the future. And this is, as I said, Hyperledger Fabric is a community owned project. So anyone in the community, even yourselves, you can write your own consensus algorithm, implement it, and contribute it back to the community. So that's the ordering service and how it reaches consensus. Then the next step in the process is now all of these peers have received a block of transactions. Let's say there are 100 transactions in this block. Now, not all 100 of these transactions may be valid transactions. Now, what are some of the reasons why a transaction might be invalid? Now, one reason why it might be invalid is because a transaction has not got sufficient endorsement. So think of it as, let's say the client application, either by mistake or it was malicious, instead of getting endorsements from E0, E1 and E2, it only got endorsements from E0 and E1. E2 did not sign that transaction. In that case, now in the validation step, when all the peers see that only E0 and E1 have signed it, E2 has not signed it, then they will reject this transaction, or they will mark that transaction as invalid. So that might be one reason why it's invalidated. Another reason why it could get invalidated is because two transactions tried to update the same data. So let's say there is a variable that had a value 100. Transaction 10 in this set of 100 transactions read that variable with value 100 and did certain operations. It might have written some amount of data. It might have written something. Maybe it modified that variable from 100 to a value of 200. So that's transaction 10. There may be a transaction, let's say 50, which also read the same data element. It's because we are only reading all the committed state. The transaction 50 will also read the value of 100. It doesn't have the value of 200 that the transaction 10 wrote because they happen simultaneously. And it tried to modify that 100 to, let's say, 50. Now, the transaction 50 has read stale data because transaction 10 has already modified the data. So that transaction 50 will be marked as invalid because transaction 50 read state that was invalidated by transaction 10. So those sorts of verifications on the read-write set is being performed by all the peers in the network. Both the endorsing peers as well as the committing peers will do the validation and will now, out of the set of 100 transactions, they will mark these transactions as valid or invalid. So in the example that I stated, the transaction 50 will be marked as invalid, whereas other transactions might go through. Now, only the valid transactions write set will be updated in the world state. All the invalid transactions will have no effect on the state maintained by the blockchain itself. So that's how the overall blockchain proceeds in terms of committing transactions. So that's the validation step, saying which transactions are valid, which transactions are invalid, and that flag of whether it's valid or invalid is included in the block itself. And now the final step is, now all the peers are going to commit the set of valid transactions. They're going to commit the block. They're going to add that block into the blockchain, and each of them will emit events. Now, the events itself in Hyperledger Fabric, you can get multiple kinds of events. For the block itself, you can get an event saying this block of transactions was committed. For each transaction in the block, whether it's valid or invalid, for both of them, you can get specific transaction level events. And it's also possible for client applications to subscribe to specific transactions. For instance, a client application can only subscribe to the transactions that it has submitted. It might not be interested in getting notifications for the other transactions. So you can get transaction level events. And it's also possible to embed events in the smart contract logic itself. So in the smart contract logic, I can actually emit an event saying this variable was modified from 100 to 200 and actually give you a business justification or the business reason why it was transferred. Maybe it might say I got funds from somewhere else and I updated my latest account balance from 100 to 200. So that business information can be embedded in an event. Those are called chain code events, and those are also part of the block and emitted along with the block events and the transaction events. So that forms the notification part of the whole transaction flow. And these notifications are on a per peer basis. So it's possible that P4 is emitting events and the same events will be emitted by P3 as well. So the client application can listen in on any of the peers that it has access to. Maybe within its organization, its organization may be running, let's say, 3 peers. It can listen to any of those peers, and even if one of those peers fails, it can get those events from the other peers. So that's the fault tolerance that the decentralized system will give you. So why did we architect it this way, right? What is the reason for having the endorsement first, then a ordering, then a validation, right? If you look at many of the existing blockchain platforms, they actually have the thing inverted around. They first do an ordering, and then they do the execution and validation of the transactions. So it's an order and then execute is the traditional way in which many people have built blockchain applications, whereas Hyperledger Fabric, for very specific reasons, we took a deviation from that. Go do the execution first and then ordering and validation. And some of the reasons are as follows, right? The notion of endorsements gives you a way for you to specify who in the system needs to validate a particular transaction. So I can specifically say these 3 organizations have to accept my transaction for it to go through. That can give you a way to embed business logic into the endorsement phase itself. So if these organizations do not accept that this is a valid transaction, it cannot go through. So that's a way in which you can embed business logic into endorsements. The second reason is to eliminate non-deterministic transactions. Non-deterministic transactions can actually play havoc in a blockchain system. What can happen if it's non-deterministic, because of the fact that these transactions are executed by all the peers or multiple peers in the network, if they all come up with different answers, then it can lead to inconsistent state across the network, and we don't want that. We want all the nodes to maintain the same consistent state at any point of time. So we want to eliminate non-deterministic transactions very early in the transaction flow. So if the 3 endorsers or how many ever endorsers execute the transaction first, they can find out that, okay, this is non-deterministic, 3 of us got 3 different answers, so we're not going to let this into the ordering at all. So it doesn't even get to the next phase, it's thrown away right there. And the other advantage of separating out endorsers versus committers and also doing the endorsements first is to be able to scale in the number of participants and really scale in the transaction throughput. So think of it, let's say I have a 20 node network. It's possible that there are 4 sets of 5 nodes. This 20, let's say it's divided as 4 sets of 5 nodes. Each of these 5 nodes can be executing a different transaction parallelly. So nodes 1 to 5 may be executing one transaction, nodes 6 to 10 may be executing another transaction, and all of these transaction executions can happen in parallel, and they can all be submitted to the ordering service in parallel, right? As long as the endorsement policy says I want 5 nodes to accept this transaction. Based on the endorsement policy, you can use that to also scale in terms of transaction throughput. You can have multiple parallel transactions going through the system simultaneously. So that was also a reason for us to adopt this first execute, then order, and then validate. Okay, so with that, I think we conclude the way Hyperledger Fabric executes transactions, achieves consensus across a distributed set of applications and users who are submitting transactions, and how a decentralized set of nodes are committing these transactions. So a couple of fun reading exercises for you at the end of this lecture. So the whole Hyperledger Fabric, its architecture, the transaction flow, along with some experimental results, has been published in a research paper recently in Eurosys this year, 2018. And the title is Hyperledger Fabric, a distributed operating system for permission blockchains. A preprint of that is available on arXiv, so you can go look at that. You can go read that. I think it's a very good paper to read to help you motivate some of the requirements from enterprise applications and why we architected Hyperledger Fabric the way we did. And extensive documentation for Hyperledger Fabric and specifically on its transaction flow is available online. And it's getting continuously improved with a lot of examples as well online. So you can go look at the documentation. It'll give you a detailed explanation of how exactly all of these steps are happening. And I encourage you all to go through that. Okay, with that concludes this lecture. So thanks a lot for your time. I'll see you at the next lecture.